Crystal singing bowls and metallic singing bowls are instruments used in meditation, sound therapy, performance, and for personal enjoyment. They're categorized as idiophones, instruments that vibrate as a whole when struck, shaken, or scraped. While they are shaped alike and played in a similar fashion, these instruments express a unique timbre from one another. In this video, we will dive into each instrument's unique sound and discuss their differences and similarities. Crystal singing bowls are a recent invention and are a byproduct of the microchip industry. These bowls are created from silicon quartz, not crystal, as their popular name suggests. Their original function was to grow microchips. A bath would be created that would pull the silicon off the walls and redeposit it into the layers of the chip. Frosted bowls are created by filling a mold with silica sand and superheating it while spinning the mold. Clear bowls are created by superheating silica, blowing and forming the mold using traditional glass blowing techniques. Crystal bowls may also be infused or coated with other minerals. Metallic bowls, also called Himalayan singing bowls, have been used for many centuries. No consensus exists as to their native origin or when they began being used for healing and sacred ritual. Some experts hypothesize that these instruments began as eating bowls and their musical properties were discovered afterwards. They are made from bronze, an alloy of copper and tin. To create them, the metal is heated, hammered by hand, and formed on a lathe until the desired sound and shape is reached. Contemporary bowls may also be stamped from a mold. However, these are often inferior in sound quality. Now we'll take a look at some examples of crystal and metallic singing bowls. All the examples are pitched in C# for easy comparison. First, take a look at a frosted white crystal bowl being struck on the spectrogram. The pitch is very steady, no warbling or modulation occurs. The fundamental frequency is 280 Hz. This low tone is often referred to as the male tone of the bowl. Above this is the second harmonic, twice the fundamental at 560 Hz. But as we can hear and see, it is very faint. The resonant frequency above this is an enharmonic overtone, meaning that it is not mathematically related to the fundamental. At around 720 Hz, it is between the second harmonic at 560 and the third harmonic at 840 Hz. This first enharmonic overtone may be generally referred to as the female tone of the bowl. Let's have a different way of looking at this. This tool is called the snail, and it allows us to easily examine pitched instruments using the Western scale. This bowl is just a bit off the standard tuning of 440 Hz, so I've adjusted it to 443. For our purposes, we are interested in the intervallic relationships between the fundamental frequency and its overtones. Here is the fundamental at C#, also known as D flat, and here is the overtone we heard, smack dab between the note F and G flat. So this overtone is between a major third and a perfect fourth away from its fundamental, if we are thinking about those relationships on a piano scale. Above these resonant frequencies, the energy drops off very quickly in the remaining overtones. They come off more as impact noise rather than sustained resonant frequencies. Let's compare this to a metallic bowl being struck, also in C#. These frequencies modulate, unlike the frosted crystal bowl, which is very steady. The fundamental frequency is also 280 Hz. Has a beating pattern that changes each time the instrument is struck. The handmade nature of these bowls creates imperfections in shape, and these imperfections manifest sonically as beating. Like the frosted crystal bowl, there is a faint harmonic above the fundamental, but it is very weak and nearly inaudible. Continuing along to the enharmonic overtone or female tone above this, and you'll notice its pitch is slightly higher at around 770 Hz. Let's check this out in the snail and see how it compares. There's the fundamental again. Notice that this time, the perceived pitch modulates with every strike. This time the overtone is between a G and a G flat. That interval is between a perfect fourth and a tritone away from the fundamental. We can also see the upper overtones, which each modulate uniquely with every strike of the instrument. When you flip between these two examples, you can hear the difference in overtone pitch distinctly. This difference in pitch is one of the defining characteristics of crystal and metallic bowls. Crystal bowls will typically have an overtone that is around a perfect fourth away from its fundamental, and metallic bowls will typically have one around a tritone away. Slight deviations from this commonality give each bowl its unique timbre and will affect how it harmonizes with other bowls. Let's examine how these instruments resonate when rubbed with a suede mallet. Here's the crystal bowl. Firstly, we can see that the fundamental frequency is very prominent and far more powerful than any other resonances. It slowly rises and falls in volume during play. As the bowl is excited, the second and third harmonics arise. They also modulate in volume slightly. The overtones, which quickly died off from the first impact, arise and are subtly audible. They are obscured by a fair amount of other overtones and noise. Let's see how this translates to the sense of pitch. We see the fundamental and the first overtone are back. As the bowl is rubbed, the fundamental modulates in volume and very subtly in pitch. And then the second and third harmonics appear, the C sharp above the fundamental and the A flat above that. If we snap over to the metallic bowl, we see that the fundamental is prominent in this example as well. Like the crystal bowl, the second and third harmonic arise during play. What is different is that this overtone is much stronger, almost as prominent as the fundamental. Like the frosted crystal bowl, the upper overtones reappear subtly, but are obscured by far less noise in this example. Lastly, in the upper range of the recording, there is some enharmonic noise from the swishing of the suede against the metal. Let's see how this all appears in our handy tool, the snail. We can see the fundamental and the overtones. As play begins, the volume and perceived pitch of the fundamental and all the overtones modulates up and down, more quickly and dramatically than in the frosted crystal bowl. There we see the second and third harmonics. When rubbed with the suede mallet, the perceived pitch of metallic bowls fluctuates much more dramatically than crystal bowls. Metal bowls are thin-walled and bend more readily as pressure is applied. Frosted crystal bowls, in particular, are thick and rigid, and therefore their surface does not bend as easily. Now we'll compare how metallic bowls sound when rubbed with a wooden mallet. Here's that same C-sharp metal bowl. This style of play brings out the female overtone. You can see and hear that it is actually louder than the fundamental. Playing this way produces a fair amount of noise throughout the frequency range. As you can hear, it can add character and texture, but it also needs to be balanced with the tone of the bowl so that it is not unpleasant or distracting to the listener. You can see that the upper overtones are also excited, but they are a bit more diffuse with the wooden mallet. Lastly, we'll take a quick look at clear crystal bowls. They have their own unique properties because they are smooth, thin-walled, and made by hand. Here's a recording of a clear C-sharp crystal bowl being played with a suede mallet. Like the frosted bowl, the bulk of the energy is found in the fundamental, which modulates in volume during play. Above the fundamental is the second harmonic, twice the fundamental at 552 Hz. Other than that, there are no additional resonances during this type of play. The smooth texture of the instrument causes it to be narrowly focused. When the bowl is struck, the the overtones produced modulate, and they also have a much longer sustain, similarly to a metallic bowl. Going over to the snail reveals that the overtone is a perfect fourth away from its fundamental, as we would expect from a crystal bowl. So with a clear crystal bowl, you have the tonality and focused quality of a frosted crystal bowl, combined with the clarity, beating, and sustain you would expect from a metallic bowl. Singing bowls, whether metallic or crystal, exhibit incredibly unique acoustic properties. While it is thought that they may have come from humble origins, their sound is powerful and useful for healing, meditation, and self-reflection. Understanding the acoustic properties of these instruments will help you to be a more judicious listener and an informed practitioner.